Hi, in this video I'm going to show you the intuitive meaning behind the dot product. Let me show you what I mean. The dot product is defined by two equivalent formulas. One way of computing it is to take the trigonometric formula, which takes the lengths of both vectors and multiplies them together with the cosine of the angle between them. Another way of computing the dot product is to introduce a coordinate system, then combining the components of both vectors in this fashion. The fact that both definitions give the same value is usually shown via an unwieldy proof involving the law of cosines. Go look it up if you wish. The problem is that both formulas don't seem to be guided by any intuition at all, and that the proof adds no understanding at all to either of them. Most students and teachers just go on according to the motto, "Shut up and calculate," as if there was no intuition to grasp here, when in fact there is. Imagine a metal plate heated to different temperatures at different places. The temperature varies steadily from cold in the lower left corner to hot in the upper right corner. How would one describe such a varying temperature? One way of doing this is to say by how many degrees the temperature changes for a given step length in the horizontal direction, let's say 3 degrees Celsius for each centimeter moving to the right, and in the vertical direction, let's say 4 degrees Celsius per centimeter upwards. Both numbers can be written in a column, which looks very similar to a vector. This is called a gradient. Just bear in mind that this vector is not a translation vector in the plane, since its components have the unit degrees Celsius per centimeter, not centimeters itself. So we stop short of drawing the gradient into the picture, since it is not clear where its endpoint should be relative to its starting point. Nevertheless, the temperature gradient allows us to find the change in temperature along any translation vector in the plane. Let's say from some starting point, we move 2 steps to the right, then 5 steps down. This is the translation vector 2 minus 5. In each of the horizontal steps, we will have gained 3 degrees Celsius, and in each of the vertical steps, we will have lost 4 degrees Celsius. So the total change in temperature is 2 times 3 plus minus 5 times 4, that is minus 14 degrees Celsius. You may already recognize this as the component formula. We will get back to this soon. We first need to settle where the temperature actually is in the picture as a vector. In order to accomplish this, let's find a vector along which the temperature does not change at all. That is, a vector that goes down just the right amount to counteract the increase in temperature along its horizontal component. This can be accomplished, for example, by moving 4 centimeters to the right, then 3 centimeters downwards. The change in temperature is 4 times 3 plus minus 3 times 4, that is 0 degrees Celsius. So along this whole line the temperature stays the same. But this is also true for any line parallel to it. These lines are called isotherms in the case of temperature. Now we can ask similarly, along which direction does the temperature change most steeply? This happens at precisely right angles to the isotherms. By rotating the vector 4 minus 3 by 90 degrees counterclockwise, we get a vector 3, 4, along which the increase in temperature is 3 times 3 plus 4 times 4, 25 degrees Celsius. This happens over the whole length of the vector, which is, remember your Pythagoras, 5 centimeters. So for each centimeter in this direction, the temperature increases by 25 over 5 degrees Celsius per centimeter. So the components of the temperature gradient, even though their units do not make it a simple translation vector, still tell us two things. The direction of steepest increase, that is the direction 3, 4, and the length of the temperature gradient is the rate of temperature increase along that particular direction. We can therefore draw arrows along the direction 3, 4 and have them represent the temperature gradient. Their length represents the rate of change, 5 degrees Celsius per centimeter. Just remember that these are not translation vectors. Their endpoints are not points on the metal plate. Their geometric length depends on the scale we have chosen to draw them. The scale chosen here is shown in the upper right-hand corner. Let's now get back to how the change in temperature is calculated along a given translation vector. One way of doing this is to split it into its horizontal and vertical contributions and multiply each by the corresponding component of the gradient. This is just applying the component formula onto both vectors. In this example, we are moving 6 centimeters to the right, each contributing 3 degrees Celsius in temperature increase, and then 2.5 centimeters upwards, yielding 4 degrees Celsius for each centimeter. The total change in temperature is therefore the dot product between both vectors calculated with the component formula, giving 28 degrees Celsius. But there's actually another way of calculating this change in temperature. We could just as well have split the translation vector into one part along the direction of the gradient and another part along an isotherm. Only the first part will actually contribute to the change in temperature. All we need to find it is to take the length of the vector, 6.5 centimeters, and the angle by which we are away from the gradient. Simple trigonometry gives the length of the component along the gradient, 6.5 centimeters times the cosine of the angle. The change in temperature occurs at the rate of 5 degrees Celsius per centimeter along the gradient, so it is 5 times 6.5 times cosine of the angle, which gives 28 degrees Celsius, exactly the same as the component formula. So this is the intuition behind the trigonometric formula, and I hope that you will now see how it must be equivalent and give the same thing as the component formula. If you want to see more videos like this, please subscribe and see you next time.